I'm Nikos, and I welcome you to the last talk of this day. Many web applications employ TLS nowadays in order to secure the communication channel between the browser and the server. But unfortunately, we all know that the truth is that server authentication has been shown to be kind of problematic. And an attacker might be able to impersonate the server to the browser by compromising a certificate authority, for example, even maybe stealing the server's private key. And even if nothing of the above happens, still the attacker might be able to fool the user, because the users are known to often click through warnings, so the attacker might be able to impersonate the server by just using an invalid certificate. So assume that we have such an attacker that can somehow impersonate the server to the legitimate server to the user. Now the attacker, if he is suitably positioned on the network, he can mount a so-called TLS Man-In-The-Middle attack, where while the browser tries to communicate with the server, the attacker intercepts the connection successfully, and then as the browser tries to issue an HTTP request, for example, to talk to the legitimate server, the attacker is able to steal the user's authentication credentials. It might be a password, but in this case, for example, it's just a cookie that authenticates the user. So the attacker steals the cookie, and then through a new TLS connection from the attacker to the server, the attacker is able to impersonate the user to the server and access and compromise the user's online account. And this actually can be used for a variety of nefarious purposes. And for example, it could be used by the attacker to spy on the user. And actually, many government agencies like the NSA are suspected of mounting such attacks in order to perform mass surveillance. So in this work, we are focusing on a very recent proposal called TLS Channel IDs, or simply Channel IDs, that is designed to resist this kind of attacks. And this proposal is interesting because it has already gained some traction, and specifically Google Chrome and Google servers experimentally support this technology. And also, I don't know how many of you are aware of FIDO Alliance. Can you please raise your hands? Okay, not so many. So FIDO Alliance is a non-profit organization where its members are a lot of high-profile companies like Google, Microsoft, Visa, MasterCard, PayPal, etc. And its goal is to essentially bring new web client authentication protocols to the world. And the specifications published by this alliance also support channel IDs as a solution to resist man-in-the-middle attacks. So in this work, we show that actually there is an attack against TLS channel IDs and similar authentication protocols that extends the usually considered attacker models. And we implemented and validated this attack. And on top of that, we propose a new solution to the problem by essentially combining channel ID-based authentication with the concept of invariance. And I'll describe later what this is about. And we implemented a prototype implementation for our solution that required us to change the source code of a Chromium web browser and also implement a module for the Apache on the server side. So in general, how can we prevent TLS man-in-the-middle attacks? Solutions can focus on either endpoint, and the most straightforward way to solve this is to prevent server impersonation in the first place. So this boils down to essentially fixing, for example, the flawed certificate authority trust model. And this is what certificate pinning and multipath probing solutions like certificate transparency, convergence, and other similar proposals try to solve. Alternatively, we could try to prevent user impersonation. This means that even if the attacker is still able to somehow impersonate the server to the user, he cannot abuse the user's credentials in order to complete his attack and perform a user impersonation and complete his attack. And this is exactly the path that TLS channel IDs and client authentication protocols built on top of them took in order to resist such attacks. So what is a channel ID, first of all? So channel ID is the public key of a private-public key pair that the browser generates on the fly when trying to connect to a specific domain for the first time. So the private key is shown here as a little key, and this never leaves the browser, of course. And the public key is shown as a little certificate, because you could think of it as a self-signed certificate. So that's why I have the certificate sign here. So assume that the browser connects for the first time to example.com. So upon establishing a TLS connection to this site, the browser generates on the fly this private-public key pair, and during the TLS handshake, it sends over his channel ID, so this certificate, and then proves possession of the corresponding private key through a signature. If this is successful, then this TLS connection is identified by this specific channel ID. Now, if the browser tries to establish a new connection to the same website, it will use the same channel ID. So the channel ID can be used to identify a TLS channel across multiple different TLS connections between the same server, the same browser, and the same server. And obviously, different browsers or clients will have different channel IDs, and this is why I have different colors here, such that the server will be able to differentiate, essentially, based on the channel ID between different clients. So channel IDs are supposed to be used throughout the user authentication process in order to resist TLS Man-In-The-Middle attacks. And we can essentially divide the user authentication process in two phases. The first phase happens when the user initially tries to log into the web server for the first time from a specific browser. And then there are second factor authentication protocols like phone auth by Cheskis et al. And the FIDO Alliance Universal Second Factor Authentication Standard that leverage channel IDs in order to resist man-in-the-middle attacks at this initial authentication step. But I'm skipping the details here due to time constraints on how exactly they do it. Now, after the initial login, the server can simply set a cookie to the user's browser, but specifically bind the cookie to the channel ID of that browser. And this we call a channel-bound cookie. Now, if this channel-bound cookie is presented to the server over the correct TLS channel ID, then the server will happily accept the request because it means that it originated from the correct client. But now, if an attacker tries to mount an attack at this point, he will still be able, of course, to fool the user and impersonate the server and steal the user's cookie. But now he cannot use the cookie to impersonate the user because the cookie will have to be presented over a TLS connection that features a different channel ID than the channel ID that is bound to this cookie. So in this case, the server will realize the mismatch and that something is wrong, and will not accept the incoming HTTP request, thereby foiling the attack. However, there is still a way for the attacker to achieve his goal, and this can be done with an attack that we call man-in-the-middle script in the browser. And it goes like this. So the browser tries to open a connection to example.com, which is intercepted by the attacker. Then the attacker, instead of going the conventional way of opening a new connection to example.com, he cannot do that because the channel IDs prevent this kind of attack. So the browser simply replies back, the attacker simply replies back to the user with, and the HTTP payload contains a malicious JavaScript originated by the attacker. Next, the attacker closes the TLS connection, the intercepted connection, and now his code, his JavaScript code, runs in the target server's web origin, because initially the browser thought that it was connecting to example.com. So this script now has access essentially to any web document belonging to example.com and can also issue arbitrary requests to this server. So what happened next is that when a next HTTP request for example.com will be issued by the browser will be forced to open a new TLS connection, but this time the attacker will not intercept it. So any HTTP request over that connection will carry the channel-bound cookie of the user, but it will be carried over the correct channel ID. So all those HTTP requests will be properly authenticated. But now notice that the attacker's code runs in the background, so runs in the browser essentially, and he has access to everything that the user can try to do with the server, or can by itself try to initiate malicious requests to the server. So essentially, the attacker transfers himself from the network to the browser and continues his attack from there. So man-in-the-middle script in the browser was missed by a number of proposals. The most recent and prevalent one is TLS Channel IDs, and all protocols built on top of it, like Phonoth and Fido UTF. But also traditional TLS client authentication does not prevent this attack, and also an older proposal back from 2006 called TLS session-aware authentication also falls victim to this attack. And the reason is that these solutions focus only on the client authentication part and completely ignore server authentication. And this means that the attacker is allowed to impersonate the server and then serve the browser with a malicious piece of JavaScript code, but which is considered trusted by the browser. And thus, the attacker can succeed in his attack. So it seems that we cannot ignore server authentication. However, we will show now that if a client authentication solution based, for example, on channel IDs is in place that prevents user credential theft and abuse, then we can still resist such attacks by simply requiring the property of invariance, which is a weaker property than authentication. And let me show you why. So I told you that TLS channel IDs prevent the conventional way of mounting a TLS man-in-the-middle attack. So this leaves the attacker with the option of doing a man-in-the-middle script in the browser attack. But now notice that for this attack to succeed, the user's browser needs to connect to two different entities during the same browsing session. And ignore caching for the time being, okay? So during the same browsing session, the browser needs to connect to two different entities. First, a TLS connection has to be intercepted by the attacker, because this is how the attacker essentially serves the malicious payload to the browser. And then at least one TLS connection has to be let through by the attacker and reach a legitimate server, because this is how, in the end, the attacker's script will be able to access information about the user's account. So our proposal is that we could try to exactly defeat this attack by making sure that the browser always communicates with does not communicate to two different entities during the same browsing session. Pay attention that we don't care if the browser connects to the attacker, but essentially what we want is that if this happens, all connections will be intercepted by the attacker. And let me show you exactly what I mean. So for example, assume that the user opens his browser and tries to connect to example.com. So if the first connection is not intercepted by the attacker, then by the property of invariance, we require that all subsequent TLS connections to example.com will not be intercepted by the attacker. On the other hand, if the attacker intercepts the first TLS connection to example.com, then the browser should make sure, by the property of invariance, that every subsequent TLS connection to example.com will also be intercepted by the attacker. If this does not happen, and for example, the first connection goes through and the second is intercepted by the attacker, or the other way around, it doesn't matter, the result is that there is an invariance violation. So the browser has talked to two different entities, and this should be detected by the browser and essentially abort the communication and stop the attack. Notice also that that this is different than authentication, because in authentication we don't accept the fact that the attacker can intercept any connection. In invariance, we do accept this fact, but we have to make sure that if this happens, then all connections will be intercepted. And that's how invariance is essentially weaker than authentication and easier to achieve, because there is the authentication requires this pre-established trust in order to work correctly, but with invariance, we don't need it. So let me quickly. So how can we actually achieve server invariance? Actually, there are many ways, but here I will just show you one. So assume that the browser tries to connect to the server for the first time. So after the first TLS connection is established, then the browser and the server create on the fly a new challenge-response pair based on two random values, RB, which is chosen by the user, the browser, and RS, which is chosen by the server. Then both entities store these values locally, and then upon subsequent TLS connections, all the browser has to do is to challenge the server and tell him, look, what is the response for RB? And then the server has to look up the corresponding response and send it back to the browser, which will check for matching. Now notice that if these two connections from the browser to the server, so if the server endpoint was the same entity in both of the connections, then this protocol should succeed. If not, and the attacker intercepted either of those, then this protocol essentially will fail, and the attack will be detected. Notice also here that the server has to store the channel, along with the challenge and response, has to store the channel ID of the browser, and this is needed for preventing essentially a relay attack that the attacker could do. But I encourage you to read the security analysis where we in detail describe how this works. Now, also in the paper, we describe a more elaborate solution that does not require the server to keep state, because if you see here, the server has to keep state per protocol instance. So in the paper, we also describe a more elaborate protocol that essentially securely offloads the server state to the client. And we also elaborate about other ways on how you might want to achieve the invariance property. So the insight of this work is that if we want to prevent man-in-the-middle attacks, TLS man-in-the-middle attacks, we have two options. If the web application uses weak client authentication, for example, conventional passwords and cookies, then we definitely need to enforce and ensure that server authentication is working properly. And that's why we could leverage solutions like pinning and certificate transparency in order to solve this problem. However, if the web application uses strong client authentication, for example, channel ID-based authentication, then in order to prevent such attacks, we simply need to enforce the property of invariance. And this is exactly what we propose with our solution called SISCA. So, to summarize, web servers, in web, servers can essentially push code to the client and ask to execute arbitrary code on the client side. And this has to be taken into account when designing protocols and systems for the web. This is one important point. And that's why, for example, channel IDs miss that and thus are vulnerable to this kind of attacks. So, and as I said, to prevent man-in-the-middle attacks, we have two options, either full-fledged proper server authentication or the combination of invariance with strong client authentication like channel IDs try to do. And in the paper, we describe in detail how this could be implemented, and also I've skipped a lot of details here, for example, on how you have to deal with cross-origin communication and other kind, or resource caching, for example, and other kinds of details that needs to be taken into account such that the server invariance property will hold in a realistic scenario. And with this, I conclude my talk, and I'm happy to take your questions.
So what is in the system that
Yes, so this is a kind of attack where essentially the server does not care the attacker does not care to reach the legitimate server and only wants, for example, to push fake content to the user or try to do some social engineering attack and try to elicit some information. Yes, this type of attack is not prevented by TLS Channel IDs and not by our solution, SISCA. Our solution is focused on the idea that the attacker wants to let the user access his account, for example, and try to read his emails or whatever, and then get this information. Because if you, for example, if the user wants to log into his webmail account and the attacker blocks all connections, then he might try to, do some social engineering with the user, but in the end he will not be able, for example, to read the user's email, for example, right? So yes, this is a different goal for the attacker that channel IDs and our solutions do not address.
Hi there, Juan Lang, Google. Interesting work, thank you. I wanted to make sure I understand the scope of the proposed solution that you have. It seems as though if the attack model is that the TLS Man-In-The-Middle can merely impersonate the server through a malicious certificate, for example, then requiring that the public key remain unchanged between TLS connections would be sufficient to combat that attack, right? The protocol modifications that you propose would be only be necessary in the case that the servers either use different key pairs or if the private key were stolen. Is that an accurate assessment?
Yes, correct. And the thing is that there are valid cases where the same domain is identified or authenticated by multiple certificates. Right. So just looking at the single certificate would not work in the generic case. So also in the paper, we briefly sketch on a solution that exactly relies on the witnessed public key during the TLS connection and also on a communication between the server and the browser, where the server tells essentially the browser, okay, these are all my keys, essentially, in the first phase. And then we build on top of that, and yes, you can achieve the property of invariance using just the public keys that the server might have. Yes, that's correct.